Hi everyone. Let me just set up a tone of the talk first. And this I'm going to give a talk a very on a very in sense it would be a very wide overview of the some of the ideas I've been thinking, and so hence it would be very thematic in nature. And also you can also you can jump in and anytime if you have questions. You don't need to wait till the end. So let me just start with the title. The title of my talk is sorry, one second. Is black holes and infalling shockwaves. So let me just spend a couple of minutes or so by just explaining what does title mean. So basically, there are two keywords in the title. The first one is the black hole, and the black hole is nothing but a solution of Einstein theory of general relativity, which is a classical theory of relativity. More specifically, it corresponds to a space-time with a region from which nothing can escape, and the boundary of that region is called event horizon. As explained in this diagram, this shaded region represents the black hole, and the boundary of this shaded region is the event horizon. And from the let's say from the origin to the event horizon, this is the horizon radius. So you can go as close as you want to the black hole, but once you enter it, you can't come back. That's what I mean by nothing can escape. And the second key word from in the title was the infalling shockwave. And this, by which I simply means a localized kind of wave of matter falling towards the black hole. And since I'm only interested for this talk, I'm only interested in the null infalling shock waves. By null, I simply mean that something which is traveling at the speed of light. You can think of the whole setup as a black hole with a infalling null shock wave coming towards the black hole, and as shown in this picture. So this infalling, this shock wave is coming towards the black hole at the speed of light, and black hole is already sitting there. So with these two things in hand, now you can ask, what is the simplest question you can ask with these two things in hand? So the simplest question you can ask is, how does this null shock, which is falling towards the black hole, affect the black hole? And okay, the naive idea would be, because everything which goes towards the black hole just gets absorbed by the black hole and nothing comes out. So the first thing would be to just guess would be to say that, oh, the shock goes in and absorbed by the black hole, and that's it. And it's more or less correct, but I wanted to just point it out that in the PC the Vaidya had already solved a similar kind of problem in which there was a collapsing matter which was forming a black hole. So following Vaidya, the answer to our question, we were just asking that how does a null shock affect the black hole? The answer of that question would be, a shock falls into the black hole, it changes the mass and size of the horizon, as shown in this figure. Initially, you have a black hole with a horizon size R1, and when you put a null shock which is falling towards the black hole, the diagrammatically it will look like this. And the end result would be a black hole in the end, but a different mass and a different horizon. And if and with a bigger mass and bigger horizon, let's say. So this is the picture we have, and also, I mean, the one thing I want to point out about this picture is that in this resulting geometry, when shock falls to the black hole and in size of mass of the black hole gets increased, the resulting geometry is not continuous across the shock. There is a discontinuity in the metric or the geometry at the position of shock, and which you can picture in this way. You can ask this question: what does an observer, which is a fixed distance, let's say, very sufficiently far away from the black hole, feel as the shock passes through it? So this is this is the diagrammatic way of answering this question. So on the left hand side, there is some observer sitting in a spaceship at some fixed radial distance from the black hole, and the shock is not yet passed through this observer. Shock is still further away from that. So he will see that the person will see that his or her weight is let's say the 10 Newton. But as the shock passes through that observer, the weight will just get increased by some factor depending on the shock and depending on the energy content of the shock. So you will see a theta function like jump in the weight, and that is what I mean by the metric is not continuous at the position of shock. And so if it is not continuous, you can divide the space-time in two regions naturally. one which is inside the shock and another which is outside the shock. So outside observer will see the different behavior, and inside observer will see the different behavior. Okay, so I just told you in the first slide that black holes are actually, whenever something goes into that, nothing comes out. So they are really black. But once you include quantum effects, the black holes are actually not black. They radiate thermally, known as Hawking radiation, as I think Omkar also pointed out this thing. So this picture gets corrected. The picture of falling null shock into a black hole gets slightly corrected if you include the Hawking radiation. The first diagram is still a black hole with where black hole is radiating at certain temperature determined by its mass or horizon radius. And now there is incoming shock coming towards the black hole, and resulting answer would be still a black hole, but with a different horizon. But now you can ask one more thing. Consider some matter field living outside the in the black hole background, or some matter field living in the black hole background. Then naively, then there exist two kind of modes in the matter fields, which are ingoing and outgoing modes. Something which is falling towards the black hole, and something which is coming going out of the black holes, which includes Hawking radiations also. So now you can actually ask a more refined question: that how does this shock now affect these modes, which are already presented outside this black hole, this infalling and outgoing modes? How does these modes get affected by this by this infalling shock? So in terms of the modes of the field, the question ultimately boils down to finding the dynamics of some field in this black hole with shock background. And for simplicity, we are going to consider the scalar field. And the equation we want to solve is this Klein-Gordon equation in this background where we have shock also, black hole background changing with changing horizon. So now the one, as I've already mentioned, that this background geometry has two regions, one inside the shock and another outside the shock. And there is one interface, which is the shock itself. So it seems natural that the way to solve this wave equation is to use the method of images, because there are two regions and one interface. So the idea is this: if you want to solve for the wave equation outside the shock, you need to put some source inside the shock, and then you can solve it. So the free wave equation becomes the source wave equation, but shock is on. If you want to find out if you want to find solution outside the shock, you need to put some sources inside the shock. And okay, the one more thing about this equation, this free Klein-Gordon equation, is that although the metric was discontinuous, but the field is continuous across the shock. That we can show by just integrating this equation twice, just as we do in quantum mechanics or Schrodinger equation. So now, now we use this method of images. I'm not going to get into the details that how are we going to find these bulk sources to get the correct answer, but the ultimate aim of our computation is to just solve the wave equation in this black hole background with the changing horizon geometry. So, I'm going to come to the results now, what we find actually. So we found that as the shock sweeps towards the black hole, it interacts with the ingoing and outgoing modes already present there outside the black hole. And what it does with those modes is actually changes ingoing and outgoing modes into the linear combination of the ingoing and outgoing modes. So semantically, what it says is that if you have an ingoing mode which was already living there outside the black hole, so when shock hits that ingoing mode, it actually changes that ingoing mode into ingoing plus outgoing mode. And with these A and B are representing the transition amplitudes of corresponding transition amplitude. And you can think of this process in two ways, the one way to think of this process is look at this process as a quantum mechanics of two-level system, where one level represents the ingoing mode, another one represents the outgoing mode. And if the shock hits that mode, as think of as some perturbation, which is changing the state of the system from, let's say, if you are initially you have only ingoing modes, it's just changing into a linear superposition of ingoing and outgoing modes. And the other way to think of it, this process is in terms of reflection and transmission. So when there are already modes which are, for example, coming, consider Hawking mode, which is already coming out of the black hole. But when shock hits that mode, that modes get has a probability of changing into either either into ingoing and outgoing. So if it changes into ingoing, it is like a reflection. The Hawking mode is getting reflected by the shock, and the other one is a transmission. And this is just to say that there exists. I mean, there exists this ADS-CFT or gauge gravity duality, which Rajesh has also pointed out on the first day. So I mean, we don't need to go into the detail, but only thing we need to consider is this third equation. So any gravitational problem in a specific scenario, I'm not going to detail what specific scenarios I'm talking about, but any gravitational problem has a dual problem in the CFT also. So what the problem we were discussing, that how the shock affect the black hole and the matter around it, is a dual problem corresponding to that gravitational problem, is that how does the strongly coupled systems behave under sudden change in temperature? So this is the CFT or the QFT problem, dual problem. And we can answer that problem also. And the answer of this above question in the QFT can be evaluated by evaluating this correlation function in the QFT by using this ADS-CFT correspondence. So yeah, okay. So now let me just end up by saying some concluding remarks. So the summary of what the talk is, we ask a certain question, that how does infalling shock affects the black hole and the matter around it as shock falls into the black hole, and ultimately the bigger black hole comes into the picture. And the answer is that infalling shock actually changes the mass and the size of black hole, and it interacts with the ingoing and outgoing modes living in the black hole background also, changing the ingoing mode into the linear superposition of ingoing and outgoing modes. And similarly for the outgoing modes also. And the future, one of the there are few future directions I will mention. The one thing is that in the whole analysis, we just consider the single pulse of light which is falling towards the black hole. We can also we can ask what happens when we take the continuum or the multiple shocks coming one after the other. And this has a motivation because we can now model the adiabatic change in the black hole geometry also. If you take multiple shocks coming one after the other, then you can model the change in geometry as an adiabatic change in the black hole geometry. And there's another future direction which says that you can replace the infalling light with some massive particles, because right now the shock is coming towards the black hole with the speed of light. If you replace it with the massive particles, and it has some speed, but with less than speed of light. And what about the rotating and charged black holes? You can ask the same question in case of these more general black holes. So yeah, I will just end up here, and thank you for listening.
Thank you, Shivam, for a wonderful talk. Questions?
Okay. Hi, Shivam. I have a very naive question. So instead of a black hole, if I have a thermal body, like a black body, and I have a shock around it, how will this be different from that, other than the fact that maybe the thermal body, like that might have some reflection on the boundary?
First of all, I mean, when a shock, I mean, when we consider a black hole and a shock, we know that when shock is going towards let's say black hole, it's going to classically it's just going to get in, and nothing's going to come out, right? That's not true. That is, let's say it's not true for, I mean, it's true for black body, but it's not true for any general star, right? So that's one difference. But most of the analysis will actually go through, apart from the fact that that once you include quantum effects, the Hawking radiation will change the picture, but classically everything will just kind of follow through. Sorry, is that?
I can talk to you later. Maybe I am confused.
What is this dual picture of this mixing of like this ingoing and outgoing mode?
Dual picture of mixing. Dual means CFT picture. It's like if you have a CFT at certain temperature which has dissipative and fluctuating modes in that system, and you perturb the system or put some energy into it so that it's now you're changing the temperature of the system. So how does this fluctuating dissipating modes are actually changing? So it says that if you have some fluctuating modes, these fluctuating modes are actually changing into going into fluctuating plus dissipating modes. So it's like that. I mean, it's very similar to that.
We are out of time, bro. Let us thank Shivam again for the talk.